All right, let's learn about the independence of horizontal and vertical motion for objects in free fall. This is a pretty tricky concept, and it's one that's important to wrap your head around because College Board likes to test you on this quite a bit. But once you get it, you'll get it. It won't be a problem. So, all right, this diagram might look a little bit confusing, but here's what I'm trying to represent here. Let's just say that I took an object here and I released it from a point, let's call it zero, and it fell under the influence of gravity for 3 seconds. Now, how far would it fall in each of those 3 seconds? Well, I would use this equation here, basically changing y equals 1 half at squared, but we'll use g for a. All right, so that, and that's, since that's 10, half of this is 5. So after 1 second, it would fall 5 meters. After 2 seconds, I would have 4 times 5, it would fall 20 meters. And after 3 seconds, I'd have 9 times 5, it falls 45 meters. So you can see it's falling a greater distance with each passing second because it's accelerating in the vertical direction at rate g. But let's just do a thought experiment. Say I can shut off gravity. There's no gravity. Now, if I just let go of this object, it's just going to sit there. It's not going to fall at all. So what I do is I give it a shove horizontally, and I throw it horizontally at a rate of 20 meters per second. Now, if I wonder how far it's going to go horizontally, what I keep in mind is there's no acceleration. And if there's no acceleration, the only equation I use for non-accelerated motion is this one here. The change in the velocity in that x direction is going to be equal to the displacement over time. Or if I want to solve for displacement, I say velocity times time is going to tell me the displacement. Now I threw it at 20 meters per second. So 20 times 1 second means after 1 second, it's traveled 20 meters horizontally. After 2 seconds, it's traveled 40 meters horizontally. After 3 seconds, it's gone another 20 meters, and now it's traveled 60. So every second is going to go 20 meters because it's traveling at a constant rate. Now, let's turn gravity back on, but throw the object horizontally at 20 once again. What we find is that both motions happen simultaneously, but the motion we can treat as being independent of each other. So we find is in the first second, it's going to travel horizontally 20, but fall vertically 5, and it will actually be here. After 2 seconds, it will travel 40 horizontally and fall 20 vertically, ending up here. And after 3 seconds, it will have traveled 60 here, 3 times 20, but it will have fallen 45 to here. So we see that the path that's taken by an object in free fall is going to be a parabola. And that's because we have both horizontal and independent motion happening simultaneously. So just keep in mind, so the velocity vector in the horizontal direction, as long as there's no friction, and usually the problems are going to give you, they say to ignore friction, it's going to remain whatever it is to start with, in this case, 10. All right. Uh, but the vertical motion is going to be accelerated. Each second is going to go faster and faster and faster in the vertical direction. So it's important to keep in mind when we're dealing with trajectory or ballistic problems where objects are in free fall in a gravitational environment, moving through the air or the surface, above the surface of the moon or whatever. What we have is acceleration in the vertical direction, but no acceleration in the horizontal direction. So again, vertical velocity increases in the vertical direction. However, horizontal velocity does not increase in the horizontal direction. And so you just have to keep that in mind when you're solving these problems. So the most important thing you can keep in mind in all of this is this. The time an object is going to be in the air in a trajectory ballistic type problem is going to be determined by its vertical components, either how high it has to fall or how fast it has been launched in the vertical direction, or what the acceleration of gravity is that we took it to a different planet, for instance. All right, so those are the only things that matter. That the time that the horizontal motion will be in the air is going to be determined by the vertical component alone. So the horizontal component doesn't have anything to do with it. So look at this. I drop the object to 0, it falls to the ground at 2 seconds. Okay, so now I take it and I say, all right, I'm going to throw it at 10 meters per second. Well, it's still going to fall to the ground in 2 seconds because that's how long it takes to fall this far, but it's going to travel a greater horizontal distance. But it's not going to be in the air any longer because this motion doesn't add to its fall time. I throw it even faster. It's still in the air the same amount of time, 2 seconds, but in those 2 seconds, it travels further. So it's easy to get confused. You see it going farther, you think it must be in the air longer, but it's not. I mean, you could literally take a rifle and shoot it horizontally and drop a bullet at the exact same time, and they will both hit at the same time. It's just the one that was shot from the gun is going to end up very far away, but it's not going to be in the air any longer time. So let's just try an example of this. So I have a ball thrown horizontally for 30-meter cliff at 40 meters per second. How far away from the base of the cliff does it land? So the first thing I have to keep in mind is I'm going to draw a picture. It's always a good idea. I'm trying to find this delta x, the horizontal position of it. And this is the vertical component of motion. So I have to use this to find time. Now, if I want to find out how far it goes here, this is the equation I would use. I would say velocity is equal to change in position over time. And so therefore, if I want to know this, I just have to say uh, the horizontal position is going to be equal to the horizontal velocity times time. But the problem is I don't know time. So I have to solve for time using vertical motion. That's always going to be the case, is the vertical motion, whether it's the velocity of the position that's going to let you solve for time. So I'm going to use this very useful equation. Make sure you know this one, right? Height equals 1/2 at squared for objects that are initially at rest in the vertical direction. And so I can rewrite this for time and I'll get this. So t in a vertical direction is going to be equal to 2h over g, take the square root. Now what I can do is I can take this expression and substitute it for here in this expression, and it becomes this. The horizontal change in position, the horizontal displacement, is going to equal the horizontal velocity, which is here, times this. All right. And once I have this, I can solve it, right? So I can say, well, I know that the horizontal velocity is 40. I know that the height is 30 meters, and I know that g is 10. You can use 9.8 if you want to, but I'm using 10. And when I do that, I see it's going to travel 98 meters horizontally. This is a classic type of two-dimensional motion problem. But let's try it another way. What if I said, all right, so the ball is thrown horizontally at velocity v off a cliff of height h. It lands distance x away from the base of the cliff. Where would it land if it was thrown at velocity 2v? This is the kind of question College Board likes to ask. So this is a proportional reasoning, but you can't solve a proportional reasoning unless you can set up the equation to see what the relationship is between v and x. So let's go ahead and do it. We just established from the last one that if we substitute this in for t in the velocity equation, we get the horizontal velocity, which we're calling x in this case, is equal to the horizontal velocity, which we're calling v in this case, times root 2h over g. So the question is, where would it land if it was thrown 2v away? So if I look at it, how are x and v proportional to each other? Well, they're directly proportional to each other. So if I double v, I'm going to double x. It's going to land distance 2x away. Let's try a different one, though. So same thing, except this time I say, where would it land if it was thrown from height 2h? It's still thrown at speed v. Well, we go back and say this is the expression that we're using. So we see now that the relationship between h and x, h is in the numerator, so it's a direct proportion, but it's direct to the root of h. So x is proportional to root h. So if this is now 2h, this is going to be root 2x. Same thing, but now we say, what if it was on a planet where we had double the gravitational acceleration? If you think about it, well, it's going to fall faster, so it should go less distance horizontally. So again, this is the expression that we've derived. Now we want to say, well, how is it that x is proportional to g? Well, it's proportional to the reciprocal of root g, right? So therefore, if g gets bigger, x gets smaller by the root of g. So if g is doubled, this should go down by root g, or in other words, it should be equal to 1 over 2 root 2x. Let's try another one, okay? These ones sometimes seem counterintuitive, but let's just think about this. So I've got a cart traveling horizontally at 4 meters per second, and it's going to launch a ball vertically at 15 meters per second as it travels horizontally. So it's going to shoot it straight up. Okay, so I want to know the answers to these questions here. How long will the ball travel upwards? How long will it travel downwards? How high will the ball go? How far will the ball travel horizontally before coming back to the ground? And how far away from the cart will it be when it lands? Okay, well, let's try each one of these in turn. Okay, so this is good because it forces us to separate horizontal from vertical motion. All right, so let's try this one here. Oh, okay. So if I want to know how long will the ball travel upwards, that's a vertical velocity. So that means a vertical motion. So I have to use an acceleration-based equation. In this case, what I know is its initial velocity. So this would be the kinematic equation of choice. which is that acceleration is equal to the change in velocity in the vertical direction over time. Uh, Now, if I rearrange this for t, I get this. Since the the final velocity at the apex is going to be 0, what I get is negative 15 over negative 10, because it's the acceleration of gravity, gives me 1.5 seconds. It's going to go up for 1.5 seconds. How long will it travel downwards? Well, if it took 1.5 seconds to go up while accelerating at g, it's going to take 1.5 seconds to come back down at g. So you're traveling the same distance with the same acceleration. So we should see it is the same. So how long is the ball in the air? I should say, so how long is the ball in the air? Well, the ball is going to be in the air for 3 seconds then. I should point that it's going to go up for 1.5 and down for 1.5. I call these up-down problems, and they're pretty common. You just need to remember that you use for the vertical velocity to solve for the time going up, and you double it to say, well, it's got to come back down. Well, what's the maximum height the ball would reach? Now, well, it's going in a direction that is vertical, and there's acceleration in the vertical direction. So the equation I have to use to solve that is going to be this one here. I know it's vertical velocity initially. I know it's final velocity here. And so I'm using this one here to solve for the change in its y position. So I know that I'll rearrange it here to solve for y. So I'll just basically take this minus this divided by 2g. I'm going to say g instead of a. And now let's just see what I've got here. So I know that the final velocity is 0 at the apex. I know the initial velocity was 15. And I know that the acceleration of gravity is 10. And I want to solve it for y. So if I just substitute in and solve for y, what I'll get is 11.25 meters is the height that it's going to reach. How far is the ball going to travel horizontally? Now, to solve a horizontal equation, there's no acceleration. So I have to use this equation. This is the only equation you use for non-accelerated motion. All right, so if that's the case, then if I rearrange this to solve for delta x, it's going to be delta x is equal to the x velocity times the time the object is in the air. Well, we use the vertical motion. It went up for 1.5, it came down for 1.5, so it's in the air for 3 seconds. So I substitute that value in here, and I see it's going to travel 12 meters horizontally. Now, how far away from that cart will it be when it lands? And the answer is it won't be far away from it. It will be right back where it was, because uh, uh, basically, since the ball's motion is 4 meters per second horizontally the whole time it's in the air, so is the cart's. They have the same horizontal motion. So although the ball will put some vertical displacement between itself and this cart, it's never going to have any horizontal displacement between itself and the cart. So since both the ball and the cart are traveling horizontally at 4 meters per second, they're both going to travel 12 meters in those 3 seconds, and it will land right back on the cart. What if I ask you to draw position versus time velocity and acceleration graphs for both of these? Let's just try this here, okay? For the vertical motion. For the vertical motion, it's going to start off with a steep slope, 12 meters per second at time 0. Halfway between, at 1.5 seconds, sorry, this is a little bit asymmetrical, that's my bad. It will come to a velocity of 0, it will stop, and it will begin to accelerate in the negative direction. So we see I have a frown, I have negative acceleration, it's gravitation, so I should get this, and after 3 seconds, it should come back to where it started. Now, if I look at this now and I take the slope, I see I start off at 15, halfway through I end up at 0. So when it came back to the car, it should be going negative 15. And as I said, since this is a negative slope, I get this. What would it be for the horizontal motion? Well, for the horizontal motion, it's traveling at a constant, 4 meters per second. So it's going to go 12 meters over the course of 3 seconds at a constant rate. Since the rate is constant, I'll see a horizontal line at 4 meters per second because the velocity is not changing and its acceleration is 0. It never got faster or slower. All right, so why don't we try one like this, and then I'll let you go, okay? So let Vy be the initial vertical velocity of a ball when it's launched from the cart, and Vx be the horizontal velocity of the cart. So I want to write an expression for the horizontal distance traveled by the ball in terms of the variables Vy, Vx, and G. This is a very standard AP Physics kind of question, and it may cause you some anxiety now, but as you get used to doing this, it becomes very simple, okay? So I say, look, this is the equation I have to use for horizontal motion. So I want to rearrange this to solve for delta x. That's what I've been asked to do. So write an expression for delta x. So I got to isolate that on one side of the equation. Okay. So if I rearrange this equation for delta x, I get this. And as I said, we're going to take delta t, and we want to, time is always determined by the vertical motion. So this is the equation I'm going to use for vertical velocity. So if I rearrange that for t, what I get is the time it takes to go up is going to be the final velocity is 0, the initial velocity is vy, and the rate of acceleration is g. But that's just the time it takes to go up. It also has to fall back down. So that's double it. So I'm going to say double this value here. So I'm just going to put a 2 negative Vy over G, and that is equal to delta T. That's how long it's going to be in the air, 2 times the initial velocity divided by acceleration. Now I'm going to take this and I'm going to put it in this equation right here, and that gives me this. Delta x equals Vx times 2 negative Vy over G. And now I'm just going to pull the negative out of it and put it here just to make it a little bit cleaner. And here's my expression. Now the beautiful thing about this is once I have this expression, I can start to answer a proportionality question. So if the car is traveling at speed Vx and a ball launched up at Vy and the ball traveled horizontal distance delta x, what would the horizontal distance be if the ball would travel if it was launched vertically at 2 Vy? So I'm simply going to look at the equation here and say, well, it looks to me like delta x is directly proportional to Vy because this has the exponent is 1 and it's in the numerator. So basically, if I double V, I'm going to double x. So the answer is 2 delta x. All right. Same thing, but now if it was on a planet where acceleration of gravity was 2g, so it's got twice as much gravity, I think it should probably travel a shorter distance. If gravity is stronger, it's going to be air less time. So let's try. I mean, this is the expression that I derived. I look at it, what I see is delta x is inversely proportional to g because g is in the denominator. So basically, x is proportional to 1 over g. So if I double g, then this is going to be 1/2 x. Hey, thanks for watching. I know it was a lot, but these problems are kind of fun to do. So hopefully you'll enjoy them.